Hey everyone, welcome to the first chapter of this course, the reservoir and the logging environment. In this chapter, you will learn to identify key formation properties and recognize different rock types. Next, we'll get into understanding the significance and types of porosity and permeability. Finally, we will assess fluid saturations and understand the effects of borehole conditions and filtrate invasion. Let's get started. The basic purpose of calling a Wireline company is to get the first look at fundamental properties that are vital for evaluating the potential producibility of a hydrocarbon reservoir. These properties include lithology, porosity, fluid saturations, and permeability. To get these valuable data, the first log to run is a triple combo, which will provide information about resistivity, bulk density, neutron porosity, and gamma ray measurements. The difference with the quad combo is that the latter includes sonic measurements. Now, let's get back to the fundamentals and begin with lithology. This is related to two key concepts, mineralogy and framework. Mineralogy refers to the assemblage of different minerals in a rock that determines its chemical properties, and the framework describes the physical structure of rock and it determines the distribution of any void space. It's vital to be aware of this because different minerals and the physical structure of rock affect log responses. For example, many sandstones contain a large percentage of mineral quartz, while others might contain equally large percentages of feldspar minerals. The log responses of these two sandstones will be different. In summary, understanding lithology is crucial for interpreting log responses accurately. Both the mineral composition and the physical structure of rocks determine how logging tools will respond. By recognizing the mineralogy and framework of the formation being logged, we can better assess the validity of the data and make more informed decisions about the reservoir's potential. Next, let's see what is porosity. It's represented by the Greek letter phi and is the measure of void spaces within a rock. Imagine if a quarter of a rock's volume is empty space, its porosity is 25%. These voids are crucial because they hold fluids like water and hydrocarbons. Simply put, higher porosity means more fluid capacity. Now, before we explore different types of porosity, keep in mind that what's important is the connectivity of the pores. Here in the images shown in blue, this connectivity is relevant because interconnected pores allow fluids to flow, whereas isolated pores do not. So we have primary porosity, formed during the initial deposition of sediments, like the spaces between grains in sandstone. Also, there is secondary porosity, which develops later due to processes like fracturing or dissolution. When we talk about porosity measurements, we also distinguish between total porosity, which includes all pore spaces, and effective porosity, which only accounts for interconnected pores. Neutron and density logs help estimate total porosity. On the other hand, acoustic logs, imagers, magnetic resonance, and core samples are great for determining effective porosity. Be aware that guided measurements of porosity comes from core samples, but often we rely on log data. Combining neutron and density logs provides a more accurate total porosity estimate, while effective porosity from acoustic logs, imagers, magnetic resonance, and core samples are key for improving our understanding of fluid flow potential. And why is porosity important? Because these estimates are critical for determining how much fluid a formation contains and its flow potential. This information helps estimate hydrocarbons reserved and evaluate reservoir producibility, especially when core samples aren't available. Keep in mind that accurate porosity data is essential for effective reservoir management and maximizing hydrocarbon recovery. Another fundamental property is fluid saturations, such as water saturation, SW, and hydrocarbon saturation, SH, which indicate the relative proportion of these fluids. SW and SH must add up to 1. By measuring resistivity and porosity, we can estimate water saturation, giving us insights into the formation fluid content. However, fluid saturations don't directly tell us the volumes of fluids that will be produced. For instance, a 25% water saturation doesn't mean 1 barrel of water for every 3 barrels of oil. Some water, known as bound water, is trapped and irreducible. Similarly, some oil might be immobile due to capillary forces or low viscosity. By combining porosity estimates with resistivity measurements at different depths, we can assess water saturation at various distances from the borehole. Comparing this saturation reveals if hydrocarbons were displaced during the mud filtrate invasion. If water saturation differs at very depth, it indicates movable hydrocarbons, which are likely to be producible. While fluid saturations don't perfectly predict production volumes, they offer critical insights. They help determine if a formation is worth considering a reservoir. Fluid saturation estimates, combined with other log data, enable clients to decide whether to complete or abandon a well. And these estimates are vital for determining a well's potential and guiding decision making. The last fundamental property covered in this module is permeability, known as the rock's ability to allow fluids to pass through it. This characteristic is vital for hydrocarbon production. We measure permeability in a unit called darcies, but often we use millidarcies, which are 1,000 of a darcy. When we talk about absolute permeability, we're referring to a rock's capacity to transmit a fluid when it's completely saturated with that fluid, meaning it's dealing with just one type of fluid at a time. However, rocks usually contain more than one fluid, like water and hydrocarbons, which are immiscible. Then, effective permeability measures the rock's ability to transmit one fluid in the presence of another. This depends on the rock's absolute permeability, capillary pressure, and the relative amount of each fluid. In consequence, more water in the pores means it's harder to transmit hydrocarbons and vice versa. And while many logging measurements respond to permeability, none can quantify it directly. Accurate permeability values come from core samples, but logs can indicate permeability qualitatively. For instance, SP curve deflections and the separation of resistivity curves can hint at permeability. Knowing the lithology and porosity also helps. For example, a sandstone with 30% porosity is likely to have high permeability, while carbonates might have low permeability due to isolated pore spaces. Advanced tools like formation testers and magnetic resonance logging, which are more expensive, provide better results for permeability estimates, often closely approximating the rock's true permeability. But remember, logs alone can't give us a complete picture. Now you will learn about how borehole properties can influence logging measurements. Since these measurements are acquired by sensors on tool strings within the borehole, it's inevitable that borehole conditions will impact the data that is collected. Some tools, like the density porosity tool, use a pad-mounted sensor equipped with collimated and shielded detectors. Collimated means that these special detectors help focus on the important signals while filtering out background noise. This design helps minimize or eliminate borehole interference, ensuring more accurate readings. However, other tools such as resistivity, neutron, and gamma ray operate with sensors surrounded by borehole fluid, making them more susceptible to borehole conditions. For resistivity measurements taken at various depths, borehole influence is more pronounced in shallow readings compared to deeper ones. This influence varies with borehole fluid salinity and diameter as well. Ideally, resistivity tools should be logged in their preferred borehole environment to minimize this impact. But since perfect conditions are rare, we often need to assess and correct for borehole influence. To determine and correct for borehole influence, we control tool position using stand-off or centralizers and measure borehole salinity and diameter. Neutron and gamma ray measurements, for example, are affected by attenuating effects of borehole fluid. More borehole fluid around the tool means fewer neutrons and gamma rays reach the detectors, and higher fluid density has a similar effect. Finally, corrections for borehole influence can be applied if borehole properties are known. This leads to more accurate formation property estimates from logs. But while some corrections are applied in real time, most are left to clients' discretion, meaning that service companies often provide uncorrected results. Again, it's crucial to recognize borehole effects to apply the right corrections. Now, let's learn another concept called filtrate invasion. First, let's imagine we have a block of rock representing our formation. Now, picture a drill bit creating a hole in this block. By the nature of this process, the hole usually gets filled with drilling mud. Now, because the formation is often permeable, something interesting happens. Part of the drilling mud seeps into the formation, and this invading fluid is called filtrate. Let's break this down further. Closest to the borehole, we have an area where the filtrate concentration is higher. This zone is heavily influenced by the drilling mode and is known as the flushed zone. But not all of the drilling fluid gets absorbed into the formation. Some of it starts to build up on the borehole wall, forming what we call mud cake. Moving a bit further from the borehole, we encounter the transition zone. This area has a mix of the original formation fluids and some of the filtrate. And finally, the furthest zone from the borehole is called uninvaded zone. This zone remains mostly unaffected by the drilling process and contains the original formation fluids. In summary, understanding invasion helps us to create different fluid distributions in the formation. Close to the borehole, the flushed zone contains a high proportion of mud filtrate, displacing original pore fluid. As we move further from the borehole, the transition zone has a decreasing filtrate and increasing original fluids. Beyond this, in the uninvaded zone, pores are filled entirely with original fluids like water and hydrocarbons, and logging measurements taken at a deeper depth reflect these original conditions. To conclude, remember that filtrate invasion, rock properties, the borehole influence, and their effects or log responses make data validation and reservoir evaluation challenging. Understanding geology helps make sense of these factors, even without an extensive geological knowledge. Considering how and why rocks differ can help validate log responses and improve our reservoir evaluation.